Hello there. Today we'll look at PonderNet, Learning to Ponder by Andrea Bonino, Jan Balaguer, and Charles Blundell. This paper on a high level introduces a recurrent architecture or a principle of recurrent computation for deep networks that essentially says the network recurrently computes its output at each step, and at each step it can decide to stop now because it is satisfied with the answer that it has. The idea is that at a complex task you can compute for many steps because it requires many steps of thinking and then give the output. And for an easy task, the network can decide to output right away because it already has computed the solution. This decision can be done on a per sample basis. So for each sample, the network can decide when it's time to give the final output. And this is not necessarily a paper that just makes something bigger and then pushes state of the art on some benchmark, and that's why it piqued my interest, is that it tries to rephrase a little bit how we think about the connection of deep learning and algorithms like classic algorithms by themselves. Essentially, this is a dynamic if condition in this algorithm that decides when it's time to stop. And I appreciate that not everything has to be state-of-the-art pushing here. This is simply a cool method to do something that's relatively new. Of course, things like this have been done before, and they are discussed at length in this paper, how this paper is different from other papers that do similar things. And it does push state of the art, just not on benchmarks that you might be super duper familiar with. But yeah, it's a cool paper. It's a short paper. The idea is pretty simple and it appears to work. And yeah, that's exciting stuff. So we're going to dive into this paper, have a look at what's new in this particular model, how it works. And yeah, as always, if you have feedback, leave a comment, subscribe. I'd be happy for that. And yeah, thanks for being here. Okay, so in the abstract here, they say that in a standard neural network, the amount of computation used grows with the size of the inputs, but not with the complexity of the problem being learned. So, which is true, right? In a standard neural network, you have a forward pass. Be that in a fully connected neural network where you have your input and then you go layer, and then you have your output. This computation here is always the same, no matter the input. Even in a recurrent neural network, right? You have kind of an input right here at the beginning, you have a layer, then you have an input again, and then you have this that goes into the same layer, and then you have the next input that goes into the same layer. Even a recurrent neural network usually just does the same forward pass. This is a little bit different if you have something like a language model that can emit at some point a stop token or an end of sentence token, at which point the computation essentially stops. But it's a little bit of a different thing than we consider right here. Right here, we consider a neural network that has to find the answer to a particular problem. And we're going to see the problems down. But one problem that they present is the parity problem. So the parity problem is you get a string of zeros and ones. I think there is also negative ones in there, but I think they're a bit for a distraction. And the answer you're looking for is, as a whole, is the parity, so the amount of ones in this string, odd or even, right? So this requires let's say an integrated view of computation. This is essentially a classic algorithm that you have to perform over this string. And neural networks, as good as they are in computer vision and speech recognition, they are having trouble with simple algorithmic tasks like this. So the idea of this paper here is that, well, it doesn't make sense to apply a neural network that always does the same amount of compute, right? I shove this sequence just like in here. doesn't make sense, because, you know, if there is just a single 1 in the string and I see that right away, I can give the answer right away. However, if it's a long string and it has a bunch of 1s, I might need to think about this problem for a while and thus adapt the number of computation steps I do in my head. I might, you know, first, if I look at this string, I might first connect these two, you know, and then that's 2. And then I might connect these two, that's 2 again. And then I might connect these two, that's 4. There's nothing here, there's nothing here, right? Okay, 4. So that's kind of like 1, 2, 3 steps of computation. So that's the rough idea. Whereas if the string was shorter and more regular, I might need less computation. So they say, to overcome this limitation, we introduce PonderNet, a new algorithm that learns to adapt the amount of computation based on the complexity of the problem at hand. PonderNet learns end-to-end the number of computational steps to achieve an effective compromise between training, prediction accuracy, computational cost, and generalization. So we are going to see how they do this. Yeah, exactly. So they go into the tasks. Their experimental tasks in this paper are sort of these constructed tasks where people know you need this dynamic computation. They're not gonna compete on like ImageNet or something like this. So a majority of the paper is in contraposing their model against this ACT model, the adaptive computation time, I believe. So there have been previous attempts at doing dynamic computation time, yet either they have, it turns out they're kind of finicky, and this model here, this PonderNet model, has a bunch of advantages. They say they present PonderNet that builds on the previous ideas. It's fully differentiable, which allows for low variance gradient estimates, unlike reinforcement. So a couple of previous attempts have been with reinforcement learning. So let's just learn the number of steps or when to stop using reinforcement learning. And that, as you might know, is very, very noisy. It has unbiased gradient estimates, which is also unlike other models in the past. And yeah, so they say this has consequences in all aspects of the model. In PonderNet, the halting node predicts the probability of halting conditional on not having halted before. This kind of seems obvious, but apparently that no one has done this so far. So what do we need for an architecture for PonderNet? They say this down here. Essentially, that's the architecture. It's an inline formula, which, you know, but that's the architecture. So what you need is you need an input, okay? You need an input, which is x, your input. And x is transformed into a hidden state. This is, let's say, the hidden state at step 1. Those two, or you can also reformulate this as just the hidden state. The hidden state is going into S, the so-called step function. And that's the recurrent function right here. So into this step function, you can put anything you want. You can put like a CNN inside. You can treat this as an LSTM since we're going to apply it recurrently. And anything you want can be the step function as long as it can be applied recurrently. So this step function is going to give you the next hidden state, right? So you can see it's a recurrent neural network. However, it is also going to give you the output at that particular point in time. So y1, I guess that'd be here. And it's also going to give you this number lambda n. Now, what are these? So from here, you could apply the step function. Again, you'd get h3, you'd get the output 2, and you'd get lambda, sorry, that's a 1, that's a 2. Okay, so it seems like it's just a recurrent neural network. And if I were to push this to the end, right, I give my h, and then at the end I get my yn, and I treat that as the output of the computation, then it's just a recurrent neural network. However, as we said, the network can, in this case, decide to stop anywhere in between. For example, if it decides to stop at this particular step, then that would be the output of the computation. So every computation step, the network computes a potential output, a suggestion for an output. And then it also thinks about whether or not it really wants to answer with that output, or whether it wants to continue and to do another step, essentially take another shot at answering the question because it doesn't yet have the correct answer. And that's where this lambda thing comes in. So the lambda is a probability of stopping, essentially. So here you can see the output lambda is a number between 0 and 1, and that is the probability of halting. This is the output considered that the network halts. So whenever this is 1, the network will halt, conditioned on the fact that it hasn't previously halted. It seems, as I said, it seems obvious to formulate it like this, because you can only halt if you haven't previously halted, but apparently previous models have simply output a number that is sort of the probability of halting in general, which doesn't give you an unbiased gradient if you try to backpropagate through it. So if you consider the lambdas to be like this, if you unroll for an entire training run, then you get the probability of halting at any particular step, this one. So this is what the previous networks would have estimated directly. However, this network estimates these lambdas, these ones here. So you can see how you can compute the probability that, for example, the network halts after 3 steps by multiplying up the probability that network has not halted, which is this one, at step 1, has not halted at step 2, and then the probability that network halts at step 3, given that it hasn't halted at the previous steps. So that is a valid probability distribution. It's a generalization of the geometric distribution. And essentially, it encapsulates a decision tree, right? So you're at the beginning, you can halt or not, or continue. If you continue, then again, you can halt or you can continue. If again, you can halt or continue, and so on. And all of this, so if you want the probability that the network halts after the 3rd step, then you would consider this node, which means that you multiply up these paths right here, and that's the probability that it halts after 3 steps. Okay, so the network can output this lambda at every step. If the lambda is high, then the network halts. Of course, at inference, this is done probabilistically. Now, at training time, this is done a little bit differently. So I hope you can see at inference time, you simply go forward and you get a lambda. Maybe the lambda in the first step is 0.1. And then you flip a coin, a biased coin, right? If it comes up heads, you stop with the probability of 0.1. If it comes up tails, which is a 0.9 probability, you continue. Then maybe at the second step, it's 0.05. So maybe you stop, but probably you won't stop. And then at the 3rd step, it comes up 0.9. The network thinks, yeah, I should probably stop here. And you sample from that, and yes, you might indeed, in 9 out of 10 cases, you actually stop there. So that's inference. How about training? So how about we train this thing? During training, what we do is, again, we input x, our input into an encoder for the hidden state. And as I said, you can also input x all the time into your step function, as you see right here. But what you do is you unroll the network for a number of steps, right? Independent of these output nodes, independent of the halting probability. Let's say we unroll it for 5 steps right here. And at every point we get a output and a value, y3, y4. This is lambda 2, lambda 3, lambda 4. So at training, we simply unroll until a given step. Now, there are some technical difficulties with unrolling for a finite amount of step, like how do you normalize the probability distribution, because essentially this tree can go on until infinity. They find, okay, we can simply unroll until kind of the rest probability, the probability we haven't used yet, is really small, and then just load that all onto the last step. But these are technical difficulties that you really only care when you then go and implement. However, so we unroll for a number of steps, and then we consider all the outputs at the same time. Now, this is one big difference, I believe, to one of the previous networks, to this ACT. So what ACT does is it always unrolls, and then the output of the network. So for ACT, the output of the network would simply be a weighted output of the lambda I, yi. So the output of the network is always a weighting between the different steps, okay? And the network can decide, okay, how do I want to weight the individual outputs? Whereas here, it's different. Here, the output is really either y1 or y2 or y3 or y4. And in order to pack this into a single loss function, what we can do, I should probably leave this. In order to pack this into a single loss function, we simply take, okay, what's the loss? What would be the loss if we answered y1, right? What would be the loss? And we weigh that by the probability. And we say, okay, what would be the loss of y2? We weigh it by the probability that the network output, right? So now if we, and so on, so plus da 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 da. So essentially we compute the expected loss given the probabilities that the network has output. So now if we backprop this, we backprop through these losses. We have, of course, 2 paths of backpropping. So we backprop through the y's, which means so there is a loss, right? And both these things and these things go into the loss, right? So the loss is, how bad is this, times how probable it was, and so on. So the backpropagation path would actually attack at 2 different paths, you can see. So the backprop goes into y because you want the network to compute a better output, but the backpropagation also goes into the lambda because you want the network to get better at estimating when its output is good and when not. This I see a little bit as a tricky situation because usually this seems a little bit unstable just from experience from other papers and so on. If you have a backprop through 2 different things, especially that appear to be multiplied together, and that the network can now trade off one versus the other, which you might think is desirable, right? It can either choose to make its output better if it wants to keep the probability high of outputting this thing, or it can just reduce the probability that it's going to output whatever it wants to output, and then it doesn't have to necessarily make the output itself correct because the loss won't be as high for that particular thing because the probability of outputting it is low. So the network essentially has a choice. As I said, this might be desirable, but usually that's kind of unstable. And I think, this is just my personal opinion, I think a lot of why this might work might rest on whether or not, or let's say the complexity itself of assessing, of making y better versus adjusting these probabilities. Of course, yeah. So you see, if the output y is very complex, right, then the same gradient signal for that might mean much less than simply reducing the probability. Okay, so if the output is very, very complex, right, not the problem, but just the output itself, right, how to arrive at an output. If the output is an entire pixel map or something like this, and that has dependencies and so on, the network might just choose to always reduce the probability, because it's like, well, how am I gonna make this better at all? I don't know. I can just reduce the probability I'm going to output this crap, right? And it will probably do this then for every single step, which if it's a complex problem makes sense, but still, that would be a bit my fear here, and this is not really discussed in the paper itself. So I think the fact that this works might rely on sort of a balance of the complexity or information content that you get from the loss at the output node versus the loss at the probability node. So, okay, enough about that. So during training, you simply compute the expected loss weighted by the probabilities, and then you can backprop through that. And I hope you can see the difference between these two. One is they both seem to sum up somehow the outputs weighted by these factors. However, one considers the actual output of the network to be a weighted combination of outputs of the individual steps, where the other one says, no, the network output is actually one of them. We don't know which one, ergo, for the loss, we need to compute the expectation of the loss. That seems to be a bit of a, let's just say, it seems to be a more reasonable formulation, though in hindsight you can say many things are reasonable if they work better, right? So they discuss things like maximum number of pondering steps and so on, again, which I think is a technical detail. And this is interesting. So there you have the training loss, as we just discussed. Now, we've discussed this part right here, which they call the reconstruction loss, because you have some kind of desired y, and you have a y that comes from this. And I was a little bit wrong here in my formulation. Of course, the expectation, you don't want to take the lambdas, you actually want to take the probabilities that each thing happens, which means that you need to compute this p number, going along this tree as we did, because the p is the actual probability that you reach that node, whereas the lambda is only the conditional probability that you reach a node given you were at the previous node. So yeah, consider that if you are crazy enough to implement things straight as I speak in the videos. Lucid Rains, shout out. The second part of the loss here, and you can see this is a hyperparameter, so you're going to trade off two losses right here, because right now we saw, okay, you can either continue or not continue, and for the network, it might actually be easier, as I said, if the loss of the output comes reasonably complex right here, it might be easier to simply say, well, in this case, I'm just always going to reduce my probabilities. You might counteract this with having this number of steps, not like maximum number of steps, but essentially this term here is what counteracts that really. There is a regularization term on these probabilities, as you can see right here. So we regularize with the KL divergence, which is a sort of a distance measure. Don't tell this to a mathematician. It's a divergence. It's a sort of a distance measure between the distribution that the network outputs for the steps and this thing right here, which is a geometric distribution with this parameter. And this parameter lambda p is another hyperparameter. So what does that mean? Essentially, if you consider here the number of steps that the network thinks, right? Thinks for. What you regularize for, this distribution right here, is a geometric distribution. I'll go something like something like this. So essentially, a geometric distribution is exactly computes this tree that we computed, right? So at each step, you can essentially stop. And the question is, after, this distribution gives you a indication after what's the probability that you stop after 1 step, 2 steps, 3 steps, 4 steps, considering the fact that in order to stop after 4 steps, you already have to have made 3 non-stopping steps. Except in the geometric distribution, the probability of continuing is always the same. Whereas in our network for each node in the tree can output a different probability. Otherwise, there'd be no point. We can simply put in the fixed distribution. Now, what that probability is of stopping at each point, that's exactly this lambda p hyperparameter right here. So you regularize for a KL for this, which means that you tell the network, look, here is a reasonable distribution of when you should stop. So you should stop. So it should be, somewhat probable that you stop after 1 step, and somewhat probable if you've already done 1 step that you stop after 2 steps, and so on. So you give it sort of a default probability of stopping after each step. So if this is 0.1, for example, you tell the network essentially, look, at any given step, there's like a default 10% chance that you should stop. I, as a designer of the algorithm, think that's a reasonable prior to have. Now, the network can decide differently. The network can decide, no, I actually want to stop way earlier, right? Like this. It puts much more emphasis on the first steps, which of course in turn, because you need to normalize, puts less emphasis on the latter steps. So the network can still decide to violate this prior if it may reduce the loss for enough. So this is, as I said, a trade-off. There are 2 hyperparameters, the geometric distribution, shape, and the amount that you regularize by this KL divergence. And so now we come into the experimental results, and these are pretty neat because I think these are straightforward experimental results. They're not super big, large-scale results or anything like this, but they show that, look, on tasks where we sort of know that this dynamic computation has an advantage, our model will outperform both previous attempts at dynamic computation and especially networks that have no dynamic computation built in whatsoever. So this is the parity task, which we're going to look at. As you can see here, the orange is this ACT, which is the previous work that they compare most with, that is most similar to them. You can see in terms of accuracy, PonderNet beats this network by quite a bit. Also appreciate the error bars in this one. They almost overlap, but they don't. So you can say that you're definitely better. And interestingly, the number of compute steps, even though, the error bars overlap as well here, but PonderNet itself needs less compute steps, which might be, I don't know why exactly that happens, but you can speculate that it is because PonderNet sort of fixes on a single, like it outputs a single answer, whereas the ACT, it outputs this weighing of things, and therefore when it outputs, let's say, the first step answer, it always needs to consider that this needs to be compatible with potential future steps. So just formulating how ACT outputs stuff, it seems like it becomes a lot less dynamic because the output is always a weighting of different outputs, and therefore the first steps, they have to they can't just output what they think is the correct solution, but they sort of already have to incorporate the future and estimate, well, if I'm going to continue computing, then, you know, there's going to be stuff added to my output right here, and they have to take this into account. So it can be, ironically, less dynamic of a network. And that's why I think PonderNet might need less steps here. I might be totally wrong, though. So this is the parity task. And specifically, they train with string lengths between, you know, so this is a string length of 1, and then string length of, before we had like 8, right? Something like this. So they train up from 1 until 49. Lengths 1 until 49. And this is a little bit important, I think, because their training set contains all of them, which, you know, this is a little bit of an experimental trick, right? So in order for your network, what you want it to learn is kind of the general principle of parity independent of string length. So you construct the training data set to be sort of a distribution of lengths of string, rather than just strings of a fixed length, and then you assess their parity. So yeah, that's maybe a bit of a lesson for if you do experiments. Construct your tasks themselves already such that they help find the correct solution, right? So they train with strings of length 1 up until 49, right? And then they try to extrapolate, which is this B right here. So this is extrapolation, where then they test. So first here they train on small strings, they test on small strings. Here in B, they train on the same small strings up till length 49. But then, as I understand it, they give it length 50 to 99 or so, or 96. It says it somewhere. Just longer strings that it has been trained with, right? And now that the setup is, you know, clear, it's clear why they did the different length strings in the training set and not just fixed length strings, because there's a reasonable chance the network does not learn to extrapolate just from one particular or two particular lengths of string. Nevertheless, they test how does the network extrapolate to longer strings. And you can see right here that ACT, even though it also has been trained on the dynamic length strings, that's 50%, right? That's pure chance. So it's a parity task, right? The output is either odd or even. So ACT just gets a pure random chance as a result, whereas the PonderNet, as you can see, has like an accuracy of 0.9, which I guess is pretty good, especially on strings that are so long you've never seen them. So what can we read from this? I'm not exactly sure. There's always the possibility that, you know, they've just trained ACT wrong or something like this, but it's also reasonable to say that just how the previous models were constructed, either they didn't learn the concept, or their output is just weird in the way ACT is, or since ACT has biased gradients estimates and PonderNet doesn't, yada yada yada. We don't know. What we do know is that in their experiments, this PonderNet was actually able to solve the extrapolation task right here. The interesting thing is that if you look at the number of compute steps done, you can see that PonderNet, in contrast to what it was trained with during inference, sorry, that's an alarm. In contrast to what it was trained with during inference it has like between 2.5 and 3 steps. Let's say 3 steps, computes for about 3 steps during inference time. That's what it decides on for the smaller strings. Yet the same model, right, trained on the same strings, this is the same model during inference time on the longer strings, all of a sudden it raises its compute to 5 steps, right? Whereas ACT, okay, ACT doesn't work in this one. It just decides to stick around 2 or 3 steps as it does in training, right? So the authors sort of claim that this is good evidence that PonderNet learns to solve the actual task right here. And as the task gets more complex, PonderNet needs more steps to think about the task. And this might be exactly what we saw, that you have some sort of a string of zeros and ones, and you learn during training, you learn how to take one of these maybe in multiple steps and get an output. But now all of a sudden you have a longer string, right? Well, so now what you can do is you can also learn an output for this one, and now you have 2 outputs, right? And now you can learn a series of steps to transform the 2 outputs here into a single output. And that might just need 1 or 2 more computation steps, which is exactly what we see right here happening. So it's a good indication that something like this is happening. I would be pondering, one might say, if how this actually happens, like what do the individual computation steps represent? Is it in fact for example, in this parity task, is the network going about this task in a hierarchical fashion? Like I've shown here. Is it something different? Is it going about it in sort of a purely recurrent fashion, where even though as I understand it, we input the entire string at the beginning, does it only look at the string position by position? Or how does this work? How does the scaling behave in general if they only show small strings, large strings, but how does it behave in general as you go up the length and so on? It would be really interesting to introspect this model a little bit more than simply showing kind of end results here of the individual tasks. Okay, what they also find is that the hyperparameter, how you regularize the shape, we've seen this up here, how you regularize this shape is that is a hyperparameter, but it doesn't seem to be terribly important. Again, they compare to ACT, which has another hyperparameter that does the similar thing, that regularizes the shape of the desired halting distribution, which they call tau. Now, tau doesn't mean a particular thing so they say it does not have any straightforward interpretation, though I guess the authors of ACT might disagree. But as you can see here, so if I draw the means, there is a region where the tau, where a selection of tau performs high, though you have to see that is all around sort of the same value of like 5e-4 or something like this. And then for the other values that you might set it for, it simply doesn't work at all. So the authors claim you have to hit this tau pretty correctly in order to even get the network to do anything. Whereas they claim in PonderNet, this variable right here, first of all, it's between 0 and 1 and not just an arbitrary value, right? Because it's a probability. And they claim that, it kind of works for most things, except this one right here, where essentially you bias the network to just output everything after one step. So the trick is for the geometric distribution, you have to take the inverse, so 1 over this lambda p, and that will give you the expected number of steps that the network would compute according to this prior. So when you put in 0.9, that would essentially be a single step that you ask the network to do. But for all the other things, well, you judge for yourself whether this here is really good. But what you can say is that, look, it goes from 0 to 1, so you have a clear range, and for most of that range, the thing seems to work okay-ish. And what they highlight is even down here, so even if they do this, even if they set lambda p to 1, or sorry, to point 1, which would essentially bias the network towards 10 steps. So that the prior is, please do 10 steps of computation. In this parity task, as I understand it, even for that point 1, you can see the network, it doesn't do 10 steps. It actually also goes towards 3, 4, or 5 steps most of the time. So the network learns to be somewhat robust to this prior distribution. I mean, I guess that's also a function largely of the hyperparameter here, where you trade it off. We don't know the effect of that just from the paper. But even, even if they set that to really low, of course, then the network is kind of robust to the choice of the lambda p, yet it's still good news, because that means would mean you wouldn't have to regularize the model super heavily in order to get it to work. Okay, they go into 2 other tasks right here. Again, these aren't tasks that you might necessarily know. They are tasks where this type of computation shines particularly. And yeah, as I said, I see the paper more as sort of an interesting task, an interesting niche task, subtask, you might say, of connecting deep learning and classic algorithms. There are a number of things that I think you can do right here to extend this. So it's completely thinkable that the loss might be a bit different, that you don't ask the network to output the direct answer at each point, but you might want to attach memories and so on at these output nodes. You might want them to output intermediate results or something like this. Another thing you could do is you could work with sort of adversarial losses instead of kind of reconstruction losses or whatnot. So you could have some sort of a GAN going on inside of this in order to decide on the stopping probability. There's lots of stuff one can fiddle around with this type of network. You can even think of crazier architectures, I don't know, Hopfield-like structures where you decide, how far you iterate, because you may not always want to iterate until fixed points. I don't know. I'm just talking crap right now. Okay. One last shout out to the broader impact statement of this paper. What a beautiful, beautiful piece of writing. So essentially, they say, well, this enables neural networks to adapt their computational complexity to the tasks they are trying to solve. Neural networks are good, but currently they require much time-expensive hardware. They often fail. PonderNet expands the capabilities. They say, look, it can do this, it can do that. Makes it particularly well suited for platforms with limited resources, such as mobile phones, which is a good thing, right? It can also generalize better. That means it's better for real-world problems. And they say, we encourage other researchers to pursue the questions we have considered on this work. We believe that biasing neural network architectures to behave more like algorithms and less like flat mappings will help developing deep learning methods to their full potential. And that is indeed the broader impact of this work. Like that's the impact it had on me, and that's the impact that it should have. I'm not like at today's conferences that might be kicked out because, of course, it doesn't say technology good, technology bad, technology biased. But, respect for that. And that was it from me. Let me know what you think, and bye-bye.